Okay, so for the people who were at my session today, I warned that this might happen, and sure enough, it happened. I stepped out, I paused the recording and stepped out of the room, and then I came back and I forgot to start the recording. So I don't have a recording of the stuff that I did in the session today to help with homework 1. So I'm going to do a quick recording of some other things that'll help you. Sorry, I don't actually have what we did in the session because I think it was really helpful, but this is what I've got. So what I'm going to do is I'm going to go over the old homework, and hopefully that'll help you figure out how to do the current homework. So let me pull that up. Alright, so this would be homework 2, I think. Yes. Hold on. Okay, so this is the old homework from a previous semester, and so maybe it will help you with the current homework. Okay, so first of all, we have to minimize some expressions to the minimum cost Boolean expressions. And before I do this, let me just give you a little heads up about minimum cost. Take a look at the following. And see which one is minimum cost. And the answer is that this one is minimum cost because it only has 2 gates. It has an OR gate and it has an AND gate. And this one has 3 gates. It has 2 AND gates and an OR gate. And so this is a minimum expression. It's what you would call a minimum sum of products. But it is not a minimum cost expression. So you want to minimize the number of gates when you are looking for minimum cost. Okay, so to minimize these, we want to use our theorems. And so I always look for things that are almost but not exactly the same. So I notice that in these 2 things that are being multiplied together, I have a not R, an S, and a not U. And in this second one, I have a not R, an S, and a not U. So those are the same, it's just in the second one I also have a plus T. So I'm going to look at my theorems, and I see that if I have right here, theorem 13a, if I have x plus x times y, that equals x. So x times x plus y, that equals x. So in this case, if I look at my first thing, not R plus S plus U, and then I look at my second thing, which is not R plus S plus U plus T, now I can rearrange them because it's commutative. This I can consider as x. That's x. So this is x times x plus t, and that just equals x. So for this first one, the 2 things those 2 last things that are multiplied together, I have s bar, and that equals not R plus S plus not U. Now, if I distribute this not S, I have not S, not R, plus not S and S, plus not S and not U. Now I can look at this not s and s, and I realized from my theorems that anything anded to its conjugate, to its complement, x and not x equals 0. So this is 0, and anything ORed to 0 is just itself. That is right here. Anything ORed to 0, sorry. Anything ORed to 0 is just itself. So then I get not s, not r, plus not s, not u. And then here's where I have to be careful about my minimum cost. If I factor out a not s, and I get not s and not r or not u, then that's a more minimum cost than the one I had before. Okay, now let's look at the second one, WXZ or WX not Y not Z. Alright, so let's see, what can I do here? I'm going to factor out a WX. And now I see I've got something, or its complement anded to something. And now if I look at my theorems, if I look at 16a, something or the complement of that something and something, so x or not x and y, equals x or y. So here I have my z is like my x, and my y bar is like my y. So this is the same as z or y bar. And let's see, is there anything I can do to this? So let's see, which is minimum cost? Is this less cost than the way we have it? Let's see, so I have the second one, I have 2 gates, each with 3 inputs to those gates. So that's 2 plus 3 plus 3 plus another, I've got an OR gate and I've got 2 inputs to that. I'm not counting my NOTs. And then this one I have I've got one AND gate with 2 inputs, and I've got one OR gate with 2 inputs, and I have another AND gate with 2 inputs. It sure looks like this one is less cost. So I would go with that one. Yeah, okay. All right, let's see what the next question is. Using De Morgan's theorem, convert that Boolean expression to an equivalent expression in which the only not operations are on single variables. So I have W or not X. W or X not Y. and I have the not of all of that. So De Morgan's theorem tells me the not of an and is the or of the nots. So this turns into this. So I start with the operation that's most on the outside, which is that AND gate. And now so it becomes the not of an AND becomes the OR of the nots. Now I have the not of an OR, and that becomes the AND of the nots. Okay, so this X double bar, that's just the same as X. But now I have the not of an AND again, so that becomes the OR of the nots. And now I have everything to where I just have a single not on a single variable. And let's see. What did I do wrong? Oh, I misread the problem. On the problem, there was originally a not on this. So if I so everything I did was fine, but if I redid this problem like this, then this becomes the not of the AND becomes the OR of the nots. This double not undoes itself. And then this is the same. This is the not of an OR becomes the AND of the nots. But then this not of an AND becomes the OR of the nots. And now that matches from the homework from before that I misread. Okay, and then the last one was to use Venn diagrams to show whether or not those two things are equal. So X and Y or not Z. And then compare that to XY or XY not Z. Okay, I'll start with this first one. So I'll draw 3 circles and a box around the whole thing. And this first circle will stand for X, and the second one Y, and the third one Z. So I want Y or not Z. So not Z includes everything not in Z. So everything not in Z. So that's not Z. And then it says or Y. So that means or means I include everything that's in either one of them. So that I did not Z. And then I can also include this because that's in Y. So what I have just drawn there, that is Y or not Z. But then I have to AND that with X. And so to AND it with X means that my answer has to include anything in my answer has to be in X and it has to be in this y or not z. And so the area that is in x, whoops, and in y or not z is this area right there, because everything in that is in x and in y or not z. So this is the area indicated by the first one. Everything in there is both in x and in either y or not in z. Okay, so now let's look at the second one. So the first part says x and y, so it has to be in both x and y. So that's x and y. So it's that, or in x, y, and not z. So x, y, and not z, x, y, and not z is this part right here. That's in x, y, or not z. And so I want the or of those two regions. So the or of those two regions is this part right here, because it can include anything that's in either one of these. So this region and the region that we came up with over here, those are not the same. And since the regions are not the same, they are not the same. If you want to see how you would write this out on your homework, I would look at the folder that has the homework from last year that has it out in more detail. But I have to stop here.